Welcome to our second lesson on vertical projectile motions in one dimension. Today our discussion will be a bouncing ball. Now, as discussed in our previous lesson, a few tips that will still help you when we're going to look at a bouncing ball's graphs is, first off, you need to make sure that you draw a little picture for yourself. And remember that that picture must have curved lines. So our object would, for example, be going up curved-wise and coming back down curved-wise. Not a situation where we'll be throwing it straight up and coming straight down. Although that is actually what's happening, we're going to draw it all with curved lines. The next thing is that you must always remember to indicate the type of motion. So whether in this case it was decelerating upwards, and remember we said although decelerating is not a scientific term, we are going to use it here for your own purposes, just so that you do not get confused with the signs. And when it comes back down, it would have been acceleration. So this is our way of describing the motion. And lastly is you always need to indicate your direction as well. So do tell yourself whether it was going up or whether it was coming down. Now let us consider the following example in order to explain the graphs. So we're going to assume that this ball was dropped from a certain height. Now when a ball has been dropped, it means its initial velocity right there is 0. Now if we drop a ball, it will actually hit the ground and bounce back up. You would know in this case that it doesn't bounce back up to its original height. So just to refer back again to conservation of momentum, if you can remember, we said that if a ball does not bounce back up to its original height, we call that an inelastic collision. So that's just seen as some additional knowledge to this question. Okay, when it does though hit the ground, we never assume that the velocity is 0. I know it might be a common thing to think that whenever a ball hits the ground, it must be 0. It's never the case for any of your projectile motions. The only place where your velocity for your ball is 0 is when it either has been dropped or when your ball bounces back up or has been thrown upwards. You know that it slows down and then it comes to a stop where it turns around and then accelerate downwards. So your ball is never 0 at the bottom, but it could be 0 when it's been dropped and when it actually turns around there at the top, which means it decelerated, stopped, turned around and then accelerated. Now that we've drawn a picture of the ball, or actually have been given one, let us go and add in the specific motion that's involved. So when a ball is being dropped, remember we said that gravity pulls down onto this ball. So for us it will be accelerating downwards. When it starts bouncing back up, remember we said that it will slow down, come to a stop. That means it is actually decelerating. And once it has reached its maximum height, turned around and start falling down again, that's what we will be calling another acceleration. So there's the 3 motions of my ball. Let us now go and consider the direction. Remember in the first case it was falling down, then it would be bouncing up, and then it will be coming back down again. Now that we've implemented all our tips into this question, let us now go and draw a displacement, velocity and acceleration time graph. Now I have for our displacement time graph just drawn ourselves a little picture again so that we can see as we draw the graph what was our motions. So I've used D for down, U for up and D for down again. Now once again you need to go and pick a direction, and I'm going to pick up as positive. That means when my ball is going downwards, it must actually be the opposite, in that case the mirror image of the motion. Now what do I mean about that? Remember our ball has been dropped from a certain height here. Let's just take that as our height. We would have then said, okay, it actually accelerates, that's the motion. Now, acceleration, you know, is that smiley face. But because it's going in the opposite direction to what I've picked up as positive, then it means I need to go and do the mirror image of that. So that line actually would bend down like this. And then at that point it hits the ground, which we can see here on my displacement time graph. From there onwards it immediately goes up again. And this is a decelerating motion. Now, because I've taken up as positive, I can just normally go and draw the graph from here onwards upward. Now, please note, you would see that I do not draw the graph to the original height because our ball did not bounce back up to its original height. From there onwards, we would have wanted to say, great, it's accelerating now, but it's not going up anymore, it's now going down. So once again, I need to do the mirror image of that part of the graph. And that mirror image will bend this line back downwards again until it reaches the ground. So this is how my displacement time graph would look like, and because I've taken up as positive, you would note that it looked pretty much like the motion of my ball when I used curved lines. Let us consider the velocity time graph. Now once again, I've just drawn our little motion over there so that we can continue looking at what's happening. It is accelerating, but because I have now, remember, taken up as positive, when it goes downwards with this acceleration, it must actually be shown in the downward spot, which is then below the zero line. So my acceleration would have looked like this, but because it's going in the opposite direction, the mirror image of this graph is seen as the straight diagonal line, but pointing downwards like this. Now your velocity time graph is very unique. You would note that we were going down now, but immediately once it hit the ground, it's going to go upwards. Now can you see though that where our graph ended was right here in the middle at the bottom somewhere, and now suddenly from here we need to be in the upward spot from the graph. So our velocity time graph is going to have this dashed line that's going to go straight up. It's not a solid line, just to show us, okay, at that point again, our velocity was now in the upward spot, and then it started coming back down again. Now remember I said that you will never have a zero velocity here at the bottom. We will only have zero velocities when something has been dropped, or when it is reaching its maximum height again before it turns around and comes back down. So note though, you can see that when our object has been dropped, its initial velocity right there was zero. And also, as our ball was then decelerating upwards, you would note that it does reach a zero velocity as well right there on my graph. So now we have actually drawn the second part here of my ball by indicating it with this diagonal line downwards here. From this point onwards, the ball is indeed accelerating, but it's now going downwards. So we cannot go and draw our acceleration graph as such. We need to do the mirror image of it. And our mirror image in this case will just be continuing straight down from this line. Note though that once again, although the ball hits the ground here, this is not a zero velocity here. It has a specific velocity and is not zero. Now something unique about this graph which you must always memorize for yourself, apart from the zero velocities that's always found here at the maximums and when something has been dropped, you would always be able though to indicate the bouncing part of a ball, and that means when it actually hits the ground as these dashed lines right in the middle. Now these dashed lines could be slightly skewed. That means that they, instead of going straight up, could happen to be go slightly skewed like this. That just indicates that there's a longer contact time between the ball and the ground. But we will consider a few examples a bit later. So as long as you just remember that when your object hits the ground and bounces, that part is indicated by our dashed line. Now let us do the last part, which is the acceleration time graph. Now your acceleration time graphs should be the nicest ones to draw, specifically for projectile motions, which includes a bouncing ball. Although there is positive and negative acceleration, note though that the only acceleration working onto a bouncing ball and a projectile motion is gravity, and that gravity is working downwards at all times with a value of 9,8. So if we decided to take up as positive, then it means this will be a negative 9,8 meters per second squared. Whether that ball is going down or going up, it will still be negative 9,8 meters per second squared.